credit if you got it right in the homework. So that's the circuit analysis, just applying KCL and KVL. But, all that said, which is the easier approach? I Norton. I Norton and V Thevenin are your friend in first order circuits. It is the way to go. That said, second order circuits are not going to be near as kind. All right. Any other questions? Everything else on the homework was good times? I should add one comment I forgot to make with regard to test regrades. One of my personal pet peeves is propagating errors. So you should not have been penalized for propagating error. If you made a mistake early on and that mistake factored into another calculation where you lost points, you should not have lost points again. So one specific place I can think of would have been the power calculation in the R Thevenin circuit, or the V Thevenin circuit. If you had the right expression there but had the wrong Thevenin values, you deserve credit. So it's an old pet peeve of mine that dates back to when I was an undergraduate, when I was taking Physics 3 and did an optics problem, completely correct except for my very first calculation where I did something like 2 times 4 equals 6. And it propagated all the way through, and I got 3 points out of 25, and I was irate. I was upset. And the instructor wasn't any help because he didn't want to be involved. So this is propagated to my adulthood. So as such, I do go out of my way to make sure that you are not penalized in such an unfair fashion. All right, so check for propagating errors. You should not have lost points. TAs don't always think about it. Other stuff, so we'll have a homework before the exam, or before the spring break, of course, next Thursday. We'll have a homework after spring break, and then looking way ahead, we have another test coming up at some point. I should say, I think this material's hard, and maybe you don't, but there's no reason not to stop by my office. I really, you're welcome to come by. My office is open on Tuesday and Friday. I have no teaching load on those days. If you don't like the scheduled office hours for any reason, by all means, come by. Send me a note. But there's no good reason not to ask for help. I know maybe you don't like approaching your professors. You prefer to go to your peers. I can understand that. I am probably faster than your peers. And more likely to help you get a correct answer. Really, I am not a mean person outside of writing tests. All right, so onward. Any other questions on the first order stuff? Because we're going to move to second order, barring any just stretching. All right, second order circuits. And so in second order circuits, we're talking about 2 caps or 2 inductors, not in series, not anything we can simplify. So this is not anything we can reduce to a first order circuit or, cap plus inductor. And this one will be our kind of bread and butter one. We'll look at various combinations of this. But we'll look at 2 capacitors and 2 inductors to some extent as well. And so there's a very classic circuit called the RLC series circuit. And so this is an iconic circuit. We'll spend a fair bit of time with it. And so we're looking at a voltage source, a resistor, an inductor, and a capacitor. And so there's our RL series circuit. RLC series circuit. And that's it. So 3 components and a source. And going back to where this all started with our first order circuits, we can ask the questions. And once again, we can ask a familiar question. Determine an expression, differential expression. For the voltage across the capacitor, for DC. Voltage across the cap. And so, well, what's our approach going to be? What tool should we use here? It's a good choice. Nothing's gone away. How are we going to analyze this? KVL, exactly. We could do KCL, it's true. But KVL lends itself a little bit more smoothly in this case. So I know I said I prefer KCL usually, but in this case, KVL really jumps out. So if we look at KVL here, with those polarities, and those polarities are, you know, are conventional polarities, but it doesn't mean current or voltages in that direction. So VR plus VL plus VC equals V source. Well, there's our parameter of interest. There's our user-defined source. So this is fairly familiar. Parameter of interest. And known source. So we control the function generator knobs, or discovery board as the case may be. And so we need VR and VL in terms of VC. And so once again, we can take advantage of our circuit properties. What's VR? Well, again, our most basic formula, VR is IR times R. Well, what type of circuit is this? It's a series circuit, so IR is equal to what? IC. And IC is our familiar CdV/CdT. So lo and behold, we have VR in terms of VC. That's a differential expression, but that's fine. That's what we're looking for. Well, VL a little bit more complicated, perhaps. We have an expression for VL. That's LdI/LdT. Right? Well, once again, it is still a series circuit. That hasn't changed in the last 30 seconds. So IL is IC. We'll do a little substitution there. And so, well, there's IC. We know again, IC is CdV/CdT. So what can we write out? This is now LC dVc by dt. And now we have an expression for VL in terms of, and it's a second order expression. Just make sure I put my little 2's in there. Since the IC is a differential term, so it's a second order derivative with respect to VC. And now we can do our substitution. LC d2 VC 2 plus, where are we? You guys are letting me forget things. Plus RC dVc dt plus VC equals V source. And lo and behold, what do we have? We now have a second order differential equation. Good times. And I'm going to rewrite this on a separate piece of paper in a slightly different presentation. And that will have meaning later. Circuit, the RLC series circuit, voltage across the capacitor is now a solved problem. That differential equation is always going to be true. We have derived it. Well, this is now a second order differential equation. It's still an initial value problem, and since it's second order, what does that mean in terms of initial values? You need two. So you need two initial values. What are they? Well, you need the C0 plus and dVC0 plus by dt. But that actually has a different interpretation. What is dVC0 plus by dt? Well, what's dVC dt? Current, with the 1 over c in there. So we could write this as 1 over c IC0 plus, which in the case of our particular circuit is also equal to what? Well, still a series circuit. Again, that hasn't changed in the last minute and a half now. So IC0 plus is IL0 plus, and now we take advantage of both our initial condition expressions or continuity expressions, current through the inductor and voltage across the capacitor. And we'll come back to this, but let's look at the differential equations a little bit more, just because I know you want to. So here's, again, voltage across cap as a differential expression. And let's consider another component. So, let's look at VR. What about differential expression for VR? Well, we're still going to apply KVL. Hasn't changed. VR plus VL plus VC equals V source. So still a handy tool to use, but now our parameter of interest is VR, and we want to get VL and VC in terms of VR. And again, we can use some of our tools. So we know VL again as LDI LDT, but now we're interested in the resistor values, but it's still a series circuit, so this is L dir by dt. And again, Ohm's law is still our friend. IR is VR over R. So lo and behold, we can rewrite this as L over R dVR by dt. So just to break things apart, this is an inductor relationship. The I relationship. I said it, but I didn't write it down. This is series concept. And then this is Ohm's law. So all stuff we've used extensively so far. And likewise, we can look at VC. Well, VC, a little bit slightly different approach, but VC is 1 over C integral IC dt, right? That was just the integral relationship. So this is still VI relationship, in this case in the integral form, for a capacitor. And so again, we've used that before in various analysis. And once again, IC is IR. So what are we left with? 1 over C integral IR by dt. And again, Ohm's law is still our friend. So these same things apply. We wind up with 1 over RC integral dr by dt. And we can plug these guys in. So that guy goes there, that guy goes there, and let's do it on a separate piece of paper so we really don't clutter things up. So we look at VR plus L over R dVR by dt plus 1 over RC integral VR by dt equals V source. Well, we want a differential equation, and we have an integral here, so what do we want to do? We want to differentiate, exactly. So we differentiate, and I'll just put a big d by dt in front of the whole thing. And do a little rearranging on the fly here. So we wind up with L over R plus d by and plus 1 over RC dr equals ds, dvs by dt. And there was someone that posed the question with regard to first order circuits. Does this mean we change our particular solution? No, the particular solution form is still the same. It doesn't matter whether there's a differential term on this side or not. When you look at the particular solution, the form takes the same form as the source. So that doesn't change. Well, once again, we can do a little bit more rearranging. Rearranging is fun. R over L dVr by dt plus 1 over LC dr equals R over L dV source by dt. And then I can go ahead and rewrite that on this page. I'll give myself a little bit more room. And I'm going to start to ponder some things. Voltage across the resistor. Well, what can we say about these differential expressions? Neglecting the source term, what can we say about the left side here? They are the same. And we haven't really talked about it yet, but differential solution has a particular solution that depends on the source, and a homogeneous, excuse me. So it's my birthday, apparently I'm going through a puberty, so that's good news. Excuse me. So, and the homogeneous term for a zero source. Well, what can I say about the homogeneous solutions for both these equations? They're the same form. The coefficients will be different, of course, but the homogeneous forms will be the same. We haven't looked at the homogeneous forms, but they are the same. Who's going to believe me if I tell you that if we looked at the inductor, it will look something like this? Who believes me? And you're right to believe me. So the form on the left side, of course, is the same. You may question this term here because I didn't derive it, and I'm pretty sure that's correct. And so, again, our differential form better be the same. Voltage across inductor. And what about the current in the system? Same differential equation. Now certainly that right-hand term varies. Here we have a second derivative, a first derivative, and no derivative, or zero focus derivative. But the left-hand differential expressions are the same for each term. Now this starts to come into the question of how do we solve these guys? Well, I mentioned that they are initial value problems. So we need information about our circuits. And we already started to touch on it, but So we need information on our initial values. And again, we could go in and say VR 0 plus, VL 0 plus, VC 0 plus, and for argument's sake, we could just include an IR 0 plus, an IL 0 plus, and an IC 0 plus. And certainly we know some things right away. We can substitute in here, oops, wrong one. This equals VC 0 minus, right? Continuity must apply. We've used this already a number of times. And likewise, this equals IL 0 minus. I'm going to squeeze that in there. So these are our known things. This is a step function that turns on at t equals 0. So what does that mean for us? Well, we've used this interpretation before. This is a 0 initial condition problem. There was no source for t less than 0. We can draw that circuit out if we so inclined and prove it to ourselves. But there's no source for t less than 0, which means our initial conditions are 0, which make these two. We can carry that through a little bit further. We know this is an RLC series circuit. We've already used this, but these two better be 0, or we've cheated because they're in series. So, series. Well, given that, what can we say about VR 0 plus and VL 0 plus? Well, if the current is 0, what's the voltage across the resistor? 0. And so, well, what does that mean about the voltage across the inductor? 10. It's 10. So there's our starting voltage across the inductor. And I always found this to be a little counterintuitive for students. So at t equals 0 plus, all the voltages across the inductor. If we think about this in terms of a DC steady state problem, so here's our initial condition situation. Well, what about as t goes to infinity? So VR of infinity, VL of infinity, VC of infinity. We can put little t goes to in there if you're so inclined. And IC of infinity. Well, since we have a step function, this is a DC steady state because we have a step function source. It turns on at t equals 0, and if we wait long enough, it approaches a DC problem. And if it's a DC problem, what do we do with the capacitor? Yeah, you open it. I heard a couple people say short. You open caps. What do you do with inductors? You better say short now because that's the other choice. If the cap is open, what's the current in the circuit? 0. So what does our circuit look like? Maybe we can draw it. Here's our little minus 10. Here's our circuit. I keep yelling at you guys to draw circuits, so I should draw them too. That's L, that's C, at DC steady state. So the inductor is a short, the capacitor is an open, and if the capacitor is an open, this is 0, and that's 0. Because everything's open. And what about, then, the voltage across the resistor? Well, once again, current is 0. Ohm's law has not changed, no matter how hard we try to change it, but no. The inductor is a short circuit, so that's got to be 0. And lo and behold, our capacitor is fully charged. So if we wait long enough, all the voltage is across the capacitor. And if we think about what's going on here, roughly, and this is very, very rough, we can look at VL as a function of time. Well, that starts off at 10. And it does something. But eventually it goes to 0. Maybe I'll draw it like this. And we'll see. I mean, it can have a number of different shapes. So it starts off at 10, and as time goes to infinity, it goes to 0. And that's consistent. We don't know that it actually has that shape. It's going to depend on the circuit. Well, our resistor starts at 0 and ends at 0, and we'll kind of leave that blank for a moment. And our capacitor starts at 0 and does something, and maybe eventually reaches 10 volts. And the resistor, well, something exciting happens in between. We don't necessarily know, but maybe it does that. We certainly have a non-zero value for the voltage at some point because current starts flowing as the capacitor charges up. But eventually it goes back to 0. And we'll see expressions that look something like this. So these are kind of initial states with possible curves associated with voltages as a function of time. What's really important here is to look at the initial conditions and then look at the final conditions for this DC step function source type of problem. Just to think about another comparable situation, a reverse situation. Let's say the source equals 10 u of minus t. You can write it out mathematically. What does this correspond to? This is a source that turns off at t equals 0. So it was on for t less than 0 and then turns off. What does our t greater than 0 circuit look like? Well, in this case, look at this. There's our resistor, there's our inductor, and there's our capacitor. And we could do the same reasoning. And I'm going to draw little polarity things. Plus, minus, plus, minus, plus, minus. Well, we can look at VC 0 minus, 0 plus, I mean, the L 0 plus, and the R 0 plus. Let me change the order, sorry. And you can say IR 0 plus equals IL 0 plus. We can write this directly since it is a series circuit. I'm going to leave myself much room there, but do I need much room? If the source turns off at t equals 0, and it's been on for a long time, t less than 0, what's the current at t equals 0 plus? 0. Why? It's at DC steady state at t equals 0 minus. At t equals 0 minus, the capacitor is open, the inductor is shorted, but the capacitor is open, no current. No current in the capacitor means no current in the inductor. And so at 0 plus, this is 0. At VC 0 plus, well, I hope we agree that's 10 volts. Because I haven't drawn out the T0 minus circuit. We've done that before, but just to save a little bit of ink. Well, that's 10 volts. And again, because current is 0, that's going to be 0 as well. So what's this? And here you want to be a little bit careful. So what's the voltage across the inductor? Well, it can't be 0 because KVL doesn't apply. So KVL is our friend. Negative 10. Exactly. So this has to be minus 10. So if this is plus minus 10, this is minus plus 10, right when it shuts off. Right when it shuts off. This is the t equals 0 plus question. So that's what we're looking at. Time equals 0 plus. So, things to pay attention to. That's the voltage at t equals 0 plus. Pay attention to how the circuit behaves. And in the long run, as t goes to infinity, what's everything? Well, in this case, the source turned off. If we have no source and we wait long enough, what are we left with? A bunch of zeros. Everything goes to zero if we wait long enough in this circuit. The capacitor fully discharges. The inductor fully discharges in current sense, etc., etc. So, that's the RLC series circuit. Now, naturally, what else are we going to have? An RLC parallel circuit. Life is fun. And again, the iconic circuit, the current source, a resistor, an inductor, and a capacitor. R, L, and C. Then we can ask the same questions once again. What's the current through the inductor, the current through the capacitor, the current through the resistor, the voltage across all those. And they're all going to have the same differential expression with the right-hand side or the source term being slightly different with associated derivatives and constants, but IL differential expression. And this differential expression is the circuit's part of this problem. Once we have the differential expression, like we'll talk about later today, it becomes a repeating math problem. So this is the circuit's part. This is where the analysis comes into play. What are we going to do? Well, let's apply KCL. And we'll call this A, the whole top of the whole top row there is one big node at A. And so, well, that's going to be IR plus IL plus IC equals I source. Current going down through the three components and up through the source, as the case may be. Well, again, here's our parameter of interest, IL, and we need IR and IC in terms of IL. So what do? We apply our circuit analysis tools. What is IR? I hope we agree, that's an R. I hope we agree that Ohm's law is still here. VR over R. But what's VR? It's a parallel circuit, so it's going to be VL over R. And what's VL? LdIL by dt. And lo and behold, we have IR in terms of IL, like it's magic. And what about IC? Well, once again, we could do similar derivation. IC is CdVC dt. And VC is VL, so we can write this as CdVL by dt. And once again, CD by dt, dL, which is L dIL dt, which is LC dIL by dt, d2 IL by dt squared. And it's starting to look a little bit familiar. Bless you. And so we can substitute all that back in. LC again. And where are we? L over R. dIL by dt plus IL equals I source. And again, a little bit of rearranging. We get a differential equation that looks kind of familiar, but not quite the same. And that's again boxable. This is the differential equation for IL. And they parallel RLC. RLC circuit. And you don't have to do this again. It's now a solved problem. And it looks similar, but be careful. We go and grab our RLC series circuits. There are some similarities. They're quasi-coincidental, but not entirely. But we have a 1 over LC term here. Those are both the same, 1 over LC, but the coefficient of the second term is different. It's an artifact of the simplicity of the circuit. We'll see a different form in just a moment. But we have a second order term, a first order term, a zeroth order term, and a source. These expressions will matter quite a bit, of course, these coefficients. So, that's it. We can move on to something perhaps a little bit more fun. Maybe. A little bit more challenging, perhaps. So how do we find the differential equation for IL in this circuit? How do we find that? This becomes, again, it's a little bit like the exercise we looked at the start of the class where someone asked me how to do phi to A. It's a fair bit of substitution. Magic, if you will. So again, we could look at A, KCL at A. And so, well, if we think about this, what do we wind up with? Well, that's IL, clearly. So we can say IL plus VA minus VC over R2 equals I source. So there's our parameter of interest. There's our source term. There's a VA and there's a VC, which is a little bit problematic. Well, what's VA? What is VA?
IS.
What's that?
IS.
Let's look at here.
IS. You look around.
Well, not exactly where I was going. But VA equals VR1 plus VL, right? Do we agree? The voltage across the resistor plus the voltage across the inductor. Looks okay? Well, that's, I hope you agree, IL times R1 plus LDIL by dt.
Where's the node VC?
Oh, it's the voltage across the capacitor. It's the voltage across the cap. Well, there's VA in terms of IL. We had a nice little substitution in there. Well, how do we get rid of that VC term? Well, VC hasn't changed. So VC, 1 over C integral IC by dt. And this is where things get a little bit funky, but what's IC? Well, it's the current going this way. There's IC, there's IL, and so actually we can plug in 1 over c integral IC equals I source minus IL. And now we have an expression for VC in terms of source, which is a known thing, and IL, which is our parameter of interest. We can plug all that back into our original expression, do a little bit of rearranging, so we can plug all that back in. An IL plus an IL R1 over R2 plus an L over R2 DIL by dt. And now you can see why this is really good times. I source minus IL dt equals I source. And what do we have here? Well, we have a second order differential expression. DIL by dt plus 1 over R2C IL, and then equals the right side, DIS by dt plus 1 over R2C IS. And that looks familiar somewhat, not quite the same, but it is a second order differential equation. And I could clean this up a little bit more like I did in the other circuits. I could multiply by R2 over L, rearrange that a little bit more, but it is clearly recognizable as a second order differential equation. And so again, once we do the circuit analysis and get it in this form or close to this form, we will see it's a solved problem. So the hard part, and you'll probably agree, is going from here to this form, finding these coefficients. And this winds up being a bigger problem, certainly a more challenging problem, perhaps. Homework problem, but maybe not a test problem. So, where does that leave us? Well, as I promised, we have something that looks like, and we'll go back and just look at a general differential form. We'll take a break in just a few minutes. So what do we have right now? Well, we can look at the capacitor, voltage, or whatever. They're all the same. We have something that looks like this. And we're not too concerned about the right side yet, but I mean, I use letters instead of our circuit components, right? And we saw some of these coefficients already for our RLC series circuit. If we want, we can add a D over there. RLC series. What was A? A was 1. B was R over L. And C was 1 over LC. We already saw those, and D was also 1 over LC. But just leaving it general in that form for a moment. BC has a solution form that's familiar. Homogeneous plus BC particular. Well, the particular solution depends on the form of the source. Nothing's changed. Depends on source. So if we're looking at step function sources, what's this going to be? Constant. We'll actually call it A3. Or any other constant, some arbitrary constant, whatever you want to call it. If you want to use bananas as constants, that's fine too. So that's going to depend on the source form. What about our homogeneous expression? Well, again, going back to our kind of little table of integral forms, they're all, for a particular circuit, they're all going to have the same homogeneous expression. But if we look at this guy, in differential equations, and maybe you did this in your differential equation class, you can always say, I'm going to guess BC homogeneous is of the form an exponential. A e to the st. You can always guess that. It's a reasonable thing to do in mathematics. So you guess an exponential form. And part of the reason is, I don't know if any of you have encountered Fourier analysis yet, but you can always break everything down into a Fourier expression. And so S will wind up being equivalent to j omega, which is the Fourier form, which maybe doesn't mean anything to you right now, but it will when you take signals or equivalent class. And so this is a reasonable approach. We can plug that in. And so coming back here, well, here's our general differential equation, and let's be specific here. We're looking at the homogeneous differential equation, which means we have no source. So we're looking at A dVc. If you want to put the h in there, that's fine. Squared plus b dVc by dt h plus c dCh equals 0. Well, for our particular guess, if we guess an exponential form for our homogeneous expression, where does that leave us? Well, let's do a little bit of math here. So we wind up with a d by dt squared a e to the st plus b d by dt a e to the st plus c a e to the st equals 0. So all I did was substitute our guessed exponential form into our homogeneous differential expression. And now I can do some derivatives. That winds up being as squared times a e to the st plus ds. And it's not ds. A e to the st equals 0. Right? I've done all my derivatives, clean things up. Well, I look at each of these bracket terms. I can divide by a e to the st, right? Those guys all go away. Does everybody agree? And what are we left with? as squared plus bs plus c equals 0. So if I guess an exponential for my homogeneous expression, and I do a little substitution in there, what do I wind up with? A quadratic. We wind up with elementary school or junior high or whatever it is as our approach to solving these problems. So, for a given A, B, and C, we wind up with some solutions. So, if I can remember what the quadratic is, S equals minus B plus or minus, let's do it right. No, I just forgot it. Minus P plus or minus 4AC. B squared. Wow, I need to break 2 over 4AC over 2. There we go. Wow, that was a little embarrassing, but so brain fart for me. So, a couple things that jump out here. We have a plus or minus. What does that mean? 2 solutions. There are 2 terms in our homogeneous expression. We have an S1 that's minus B, doesn't matter what you choose, B squared minus 4AC over 2A, and an S2 that's minus B minus B squared minus 4AC over 2a. And so, well, our homogeneous solution then is going to have two expressions. An A1 e to the S1t plus an A2 e to the S2t. Sort of. There will be an exception here, a special case. All right. We'll take a short break here. Let me get my thoughts back in order so I don't do that again. And go stretch your legs. Change that a little bit now. So to go back to our voltage expression, for our particular problem we had R over L. And then 1 over LC, B source. And I wrote this just a moment ago as A, B, and C, but I'm going to be a little bit more circuit specific now and rewrite this in general. Two alpha dVc by dt plus omega naught squared. So rather than use A, B, and C, we knew A was 1. We said that. And right now, looking above, we have 2 alpha equals R over L. And at the moment, these are just kind of randomly chosen values, but clearly not random. And so these have particular meanings in our circuit analysis. We'll see alpha is called the attenuation constant. And omega naught is the resonant frequency, which doesn't mean much to us now, but will have more meaning for us in Unit 3 when we look at AC steady state. So again, all I've done was taken that A, B, and C and kind of renamed them 2 alpha and omega naught squared. And now they'll actually have some physical meaning. So we can go back and say, in our expression, if we again plug in VC homogeneous T, well, that's going to give us an S squared plus 2 alpha S plus omega naught squared equals 0. So just taking that expression that we had written out a few minutes ago, which I misplaced, but anyway, where we substituted in that AE to the ST into our homogeneous expression and got the A squared, or AS squared ds and C. Here's our new expression. This has a little bit more direct physical interpretation. So in our quadratic expression, A equals 1, B equals 2 alpha, and C equals omega naught squared. And so what are we left with? Well, S equals minus B, which is minus 2 alpha, plus or minus what's that?
It's alpha squared minus 4.
It's 4 alpha squared. It's b squared.
B squared minus 4a sweet, right?
You're correct. So it's alpha squared minus.
I don't like the quadratic equation. So there's our expression. We can do a little bit of simplification there. You can cancel out some 2, and bang, we're left with where I wanted to be all along. And there's a boxable expression. If we get the differential form, our S terms are found here. So here's the magic trick. Once we get the differential form, from differential form, find alpha and omega naught. And so that's what we did in the RLC series circuit, the RLC parallel circuit, and then that other more complicated R1, R2, L, and C circuit. Once we have the circuit in this form, this is 2 alpha, this is omega naught squared. That was our series, RLC series. Once we get this form, everything becomes a solved problem. So just to write this out, again, RLC series, we're always going to have an expression, whatever it is. I'll just leave it general. And this could be current as well. And I'll just leave this as parentheses. It depends what we're talking about, whether it's the resistor, the capacitor, and the inductor. In this case, 2 alpha equals R over L, and omega naught squared equals 1 over LC. Once we have it in that form, we can go to our quadratic formula and get these terms for S, and I'll show you what we mean, what we're going to do with those in just a second. But we'll look at the RLC parallel for a moment. And again, we can look at current in this case, and I can leave it general once again. And again, some source term on the right side, in this case 2 alpha equals 1 over RC, and omega naught squared equals 1 over LC. And we can go on and on. Any second order circuit is going to break down into some sort of coefficient that's 2 alpha and some sort of coefficient that's omega naught squared. And you get that by having a leading coefficient on your second order term of 1. So that's why early on I divided by this term to get a 1 here and get this effectively as our 2 alpha term and this as our omega naught squared term. So do the circuit analysis to get the differential expression. Once you get it in that form, then you can stop thinking about it as a circuit. So this is the circuit analysis. This becomes the mathematical process for finding our final value. So what does that mean for us? Well, we have a couple of case studies here. In general, again, what we're saying is VCT equals VC homogeneous plus VC particular. Nothing's changed. This is going to give us our homogeneous expression, but not quite as nicely as it did with first order terms. What are my possibilities here? I don't have any constraints on my R's, my L's, and my C's. So if I think about this, I have 3 possibilities with regard to this radical, right? There are three possibilities. What do I have? One of them's a lie. We have alpha greater than omega naught. Right? That's a possibility. For our series circuit, what does that mean? Well, R over 2L larger than square root of 1 over LC. Alpha greater than omega naught. These are both squares. In this case, what does that mean? Well, square root of alpha squared minus omega naught squared greater than 0, right? So if alpha is greater than omega naught, then the radical has a real value. And we have 2 possible solutions. S1 is minus alpha plus square root of alpha squared minus omega naught squared. And S2 is minus alpha minus alpha squared minus omega naught squared. Right? I mean, it goes back to the quadratic formula. What does that mean for us? Well, under this condition, we can say VC, or any B of t, or I of t, or whatever the case may be, is an A1 either the S1t plus A2 either the S2t plus VC particular. And again, this is going to be a constant term if we're looking at step function sources, nothing's changed. Here, what's wrong?
Why did you write that in parentheses right there? Was that just like-
Oh, I just said it as an example.
Okay.
That's an example.
I was sure it was-
So, correlating back to the series circuit, that just means R over 2L is greater than 1 over square root of LC. And we'll use that a lot. So, based on the what alpha and omega naught are for the RLC series circuit. And so what do we have? Well, another thing to notice here, I hope we agree that this is real and this is real. So this is going to be negative. S2 is going to be negative. We have negative, negative, right? S1 is also going to be negative. The square root of this term is going to be less than this term. So effectively, what are these two terms doing? They're exponentially declining terms. So we have to plug in numbers, of course, to find out what S1 and S2 are. But S1, S2, less than 0. And so these are exponentially decaying terms. And again, these are the transients. So this is not so dissimilar to what we saw with the first order term. We had a homogeneous expression that was exponentially decaying. You throw the switch, you get some excitement, eventually that transient fades away and you're left with a DC expression. And so that's what we see here. If we threw the switch, well, we get some initial transients. We wait long enough, those transients vanish, and we would get the DC term finally. And so there's a very similar thing for a step function source. We wind up with some v of t, a1 either the s1t plus a2 either s2t plus a3. And that's why I said a3 earlier. And that's a solved problem now for the special case where alpha is larger than omega naught. This has a name, I heard someone say it. This is called the overdamped case. That's an important thing to know. If it's an overdamped response, the homogeneous, you have two homogeneous terms and they're both exponentially decaying. If you look on the back of the handout that went out, here's an example of an overdamped case. It looks just like our first order response. So we throw a switch, we turn it on, it's overdamped. To think about this physically, let's come back to physically. So let's look at another situation. What about alpha less than omega naught? Well, in this particular case, then what's true about alpha minus omega naught squared? It's imaginary. And so when I write my S, well, I can still write this as minus alpha plus or minus, and I can do a little bit of rearranging. I'll write it as J omega naught squared minus alpha. If you don't know what J is the square root of minus 1. All those who've used I as the square root of -1 as your imaginary number, get over it. You are now electrical engineers, and electrical engineers use J. So for those of you who are math majors, I guess you're going to have to switch back and forth, but electrical engineers use J, and I will use J. So J is the square root of -1. I factored out a -1 and I reverse the order here.
Squared,
Oh, an alpha squared, yeah. Thanks. And actually we reduce this, and this has a term called beta. And I somewhat call this the oscillation frequency. And so there's our two terms. We still have two S's, an S1 and an S2. So we can write S1 equals minus alpha plus J beta, and S2 equals minus alpha minus J beta. So we still have two S's, but now they're complex. And we can go ahead and substitute those in. We still have dC of t equals an A1 e to the minus alpha minus J beta t plus an A2 e to the minus alpha plus J beta t plus an A3 if it's a DC term. Again, this depends on the particular solution. If we're looking at step function sources, it's just a constant. And this is kind of a solved problem. To go back, actually, I didn't put a box around this, but for the overdamped case with the step function source, box that up. That's the solution. So that's what you're going to work off of. And we'll have to be a little bit more specific about numbers on Monday next week, but that's a boxable solution. Well, this is also kind of a boxable solution, except we have complex numbers, and we're not used to solving with complex numbers yet.
T is on the outside and 1.
No, yeah, sorry.
Okay.
Too much carelessness today. They're both times t, of course. Since this is S1, and that's S2. So, well, I personally love complex numbers, partly because I'm an electromagnetics guy. And you will too at some point in your life. But for the moment, let's rewrite this one more time. Well, before we do that, anybody know what we can do here? Cosine beta t plus j sine beta t. What is this? Euler's law. So we actually can reduce a complex exponential into a sinusoidal term. With a little bit of trigonometric manipulation, we get a better expression. I think it's better. It's certainly easier to work with. E to the minus alpha t, A1 cosine beta t plus A2 sine beta t plus A3. What do we have here? We have exponentially decaying sinusoids with a DC term, of course. So that particular solution is off by itself, as it should be. Here's our homogeneous solution once again. And as it should with our transients, it decays to 0 as time goes to infinity. This term again becomes exponentially large, but it oscillates. And we talked about this before. This is a single sinusoid. It just has a phase term and a magnitude. But I like to write it like this because I think it's much easier to solve, and we'll see that next week. So, this is now a solved problem again. we can box this up. And to remind ourselves, this was the case, alpha was less than omega naught. And that also has a special name. It's called the underdamped case. So alpha greater than omega naught, we're overdamped. Alpha less than omega naught, we're underdamped. A nice way of thinking about these things. What does underdamped and overdamped mean? Well, you can think about resonance in some sense. If you hit a bell with a mallet or whatever, it rings, right? And if you wait long enough, that ringing kind of fades away. That's an underdamped case. So you hit the bell, it oscillates back and forth, but over time, the sound fades away due to internal friction or whatever the case may be, and it fades away. So here's the oscillation, here's the exponential decay. On the other hand, if you take a big bell and you put a block of wood in it, and you hit it, what do you get? You get kind of a thump. So kind of like, actually oscillated a little bit. But. So that's the overdamped case. No sound, just a kind of very slow convergence. And again, to go back to the handout that I was given, here's oscillation. Now clearly if it was ringing, you get a lot more oscillation. But here's oscillation that's exponentially decayed and converging to a DC value. On the other hand, here's our overdamped case. And everything's labeled, so in the handout. And so you would hear this ringing, but eventually it converges to a DC case. So very, very real things here. And then there's the critically damped case, which is a special case. So we have one more possibility. Alpha equals omega naught. And that's called critically damped. And in that case, well, what do we have? We have S equals minus alpha plus or minus 0. But we still have two solution terms that we need. And so what are we left with? Well, our voltage, and again, this could be current, this could be anything. And A1 e to the S1t, which is minus alpha, plus A2t e to the S1t, plus A3. Here's our DC step function term. Here's our homogeneous expression. Terms, and here's our particulars. This is a special case. Alpha equals omega naught. Well, again, for our series example, series RLC circuit, what does that mean? R over 2L equals 1 over LC square root. This is 2 alpha, this is alpha, and that's omega naught. And something similar for the parallel circuit. What is the critically damped case? Is this real? Well, on paper it's real. But can you really match up an R, an L, and a C so that they're equal? I mean, really? I mean, it gets a little hotter, your R changes. All right, not a lot. Maybe only in the 8th digit, but it still changes. So what does the critically damped case really represent? Well, it represents two things. It gives me another problem to assign to you. But more practically, it represents a boundary between overdamped and underdamped. So if this moves this way, we're overdamped. If it moves that way, we're more underdamped. And so really that's what the critically damped case is. It's the boundary between overdamped and underdamped. As a graph, it looks kind of like over-damped. I don't know why I left space in there, but in a physical sense, it doesn't exist. In a mathematical sense, it means I give you more problems. So this is a kind of a special case. So, to summarize, alpha greater than omega naught, let's see, step function sources. Let's be specific here. Arbitrary problems, arbitrary second order solutions. So whether it's voltage, current, whatever you're looking at, you can do the same thing. Alpha greater than omega naught, V of t, comma, I of t, whatever the case may be, it goes to an A1, either the S1t plus A2, either the S2t plus A3. That's boxable. Alpha equals omega naught. And again, this could be anything. It goes to an A1, either the ST, which is just minus alpha, we saw that. A2t, either the ST plus A3. And that's boxable, and we can add even what S's are. S in this case is minus alpha. S1 in this case is minus alpha plus square root of alpha squared minus omega naught squared, and S2 equals minus alpha minus alpha squared minus omega naught squared. And that's boxable too. We're boxing up a lot of stuff. And then finally, alpha less than omega naught, V of t, comma, I of t goes to some, either the minus alpha t, A1 cosine beta t plus A2 sine beta t plus an A3. And again, A3 is from our step function sources. And again, that's possible. So all these solutions, no matter what we're looking at, once we know alpha and omega naught, and you get those from the differential equation, so you do need to know what the differential equation is. And beta, just for completeness, omega naught squared minus alpha squared. Where in all of these, alpha, omega naught, determined from coefficients in the differential equation. So, as far as our process goes, the first thing we do is find our differential equation. And for the RLC series and RLC parallel, I've done that for you. I mean, we boxed those up earlier. Use those expressions. I mean, you can rederive them if you want. I don't mind. It's a good exercise. But we've solved it. You don't have to do it. Now, I may give you one that you do have to solve yourself, but for those classic expressions, we've done it. You found alpha and omega, so as far as our steps, find differential equation. From circuit analysis. And I can write RLC series, RLC parallel. Already done. Take advantage of it. You don't have to reinvent the wheel this time. Once you have the differential equation, determine the damping. And those are the three cases we just looked at. So, well, maybe they're filling. Determine alpha and omega naught. So we'll just write that as a separate step. Once you know alpha and omega naught, determine damping. And that gives us our solution form. Just to point out, here's our solution forms. These guys don't change if our source is different. The only thing that changes if our source is different is A3. And we saw that with the first order as well. So determine the damping, that gives us our solution form, whether we're looking at an exponential with real values, an exponential and a t times an exponential, or a decaying sinusoid. Whatever the case may be, you pick the correct one based on the relationship between alpha and omega naught. Once you're in that form, what are we going to do? Well, you solve. You need to find the coefficients. A1, A2, and A3. How are we going to find those? Well, one of them is the same as the first order. For our DC step function sources, what do we know? Well, that's the second step, but if we have a step function source, one of these we can always do quickly. Which one can we always do fairly quickly? A3. So for our step function sources, and that's what we said on the previous page, you know, step function sources, we can say step function sources, A3 from DC steady state analysis. So you can get that by just drawing the DC steady state circuit, finding the current or the voltage or whatever the thing of interest is as time goes to infinity, the same way you did with first order circuits. Nothing's changed there. How do we find A1 and A2? We call that 4A. A1 and A2 from initial conditions. And this is where we have to go back and look at the circuit directly to find out what our initial conditions are based on whatever we're asking about. So, like we saw in our early on in our RLC series circuit, let's start to set this up and pick it up again on Monday. The RLC series, well, DC, B source, if we're asking about VC as a function of time, what does that mean? We need two initial conditions. We need VC 0 plus and dVC 0 plus by dt, which we know is IC 1 over C, IC 0 plus, which is 1 over C IL 0 plus. This is from the series. So there's our two initial conditions, and we can apply those. How does that play out? Well, let's look at the overdamped case. We'll call it after that. Maybe I'll give you a couple of minutes back. So if we looked at the overdamped case, well, we can say VC of t then is A1 either S1t plus A2 either the S2t plus A3. If we're again looking at some step function source, which we've said so far, B naught U of t, just leave things symbolic for the moment, we can do what we did before. As t goes to infinity, and let's remind ourselves, S1 and S2 are less than 0. So we are dealing with general formulas right now, but we know those are negative. We talked about that a few minutes ago. So they are less than 0. So what does that mean? Well, BC as t goes to infinity, we already said this, equals 0 plus A3 equals DC steady state value. And again, you have to go to the circuit analysis to find out what that is, but we've done that a bit in the previous number, so we're somewhat familiar. VC 0 plus equals VC 0 minus. That's the continuity. So you do need to know what the initial condition is, of course. If we have a step function source, this is 0. Nothing turns on. But what does that mean? A1 plus A2 plus A3. Right? Just substituting t equals 0 in there. No problem. And what about DVC 0 plus of VC? Well, as we said, that's 1 over C IL 0 plus in this particular circuit. And that's specific to this circuit. We'll look at the parallel circuit next class. What does that mean? Well, that's A1S1 plus A2S2. And that's it. So what do we have? 1, 2, 3 equations and 3 unknowns. Thus, our 3 coefficients are found. And we'll do this a lot next class, so we'll pick that up there. You guys are over 2 minutes. Go long.
You put your phone on airplane mode so it works.
So what? Oh shit, it is.